Alright. So this wide open, like always. I have the answer key. I'll give that out in just a little bit. Just to heighten the anticipation. Anything from homework, anything from practice tests, any general procedure stuff?
Section 3.5, number 39.
3.5, number 39.
When you find the y prime, do you still leave that x prime, or do you just put that as one? Well, for the x.
If they don't say, if they just say derive this implicitly, or they give us a function of y with a relation that's got y and x in it, we always assume y is a function of x. We saw one example where it was the other way around. They wanted us to find dx, dy, x is a function of y, but they have to be really explicit about that, right? They have to really tell us that. If they don't say, then I'm assuming y is a function of x, which means y prime is I don't know, so it shows up, but x prime is 1. Yeah.
So if you do that, your answer ends up with a y in the answer of the derivative. You have to go back up to the original equation, solve for y, and plug it in for y.
Here is my answer to that. I'm hoping that there should have been a problem that I assigned that said do it both ways. Right? All right. Because you would truly only use implicit differentiation if you were either unable to solve for y, or you just really didn't want to, right? And there's two situations where you don't want to. It's just too much crap going on. I think I could solve for y, but screw it. Let me just do this, right? And then it doesn't matter because you can just plug an entire point in to get your derivative, your slope at a point. You with me? So really, overall, it doesn't matter. But there's also the other thing. I was talking to somebody else about how do you find this guy's derivative. And does anybody remember the problem with this? It's not x times x to the x minus 1. That's not right. Do you see where that would come from? That would be like x squared is 2x to 2 minus 1. Because I have a rule for this, and I have a rule for this. And those two rules are not the same. And I have both of them going on up there. You with me? That's the problem. I don't have a rule for that. So this is where I use, anytime I have something in the power that I don't want up there, log, right? In fact, everybody likes it log. So if I do that, the x comes down. That's a really old reference to write a sticky there. And now I can do this implicitly. That would be another situation where I have an explicit function of y, but I don't have a freaking clue how to take its derivative. So I use something to help me rework it. I know how to do all those derivatives now. I have to do it implicitly. You guys with me? So normally you would only do implicit if you can't untangle the y and x. Unless two things. You don't feel like it, because who cares? Or you need to rewrite the original problem and make it tangled just to be able to do any derivatives in the first place. Does that make sense? So going back to your original question, which I completely forgot by now. I think I answered it.
Would that r over y just be 1 over y?
So now if you do prime, what would it be? Careful.
1 over y?
1 over y is a good start.
Times y prime.
Times y prime. And it's a product rule, blah, blah, blah.
Okay.
Okay, I think we did that one last time.
Same rule still applies with the y. With the natural number.
Yeah, exactly. The rules don't care what's in there,
Okay.
right? The rule is always there, always.
So, you saying this one applies to number 39 on 3.5?
3.5, number 39.
I think, this is a separate question, I think.
Okay.
Yeah, 39 was, 39 led me to a question about this. Did I answer your question?
I think so. We'll find out test time.
Because your question was more like, do you always have to plug back in for y?
Well, the question says calculate y prime.
Where's this?
On exercise 8, on the chapter 3 review from the
Oh.
review.
Oh, so exercise, okay, gotcha. 262.
265.
5, thank you, yeah. I don't know if you guys got that email while I'm thinking about it. Thank you for reminding me. Number 5 references page 262. That was actually the earlier edition of this book, because I'm actually using a practice test from back in fall 2009 when I last taught Calc 1. So the new edition just moved all the pages over a few. Right? It's not a straightforward transformation, but in this case it was 3 pages later.
So my question
number 8
was,
can you solve for y? If you can, you're a better man than me. I'll tell you that.
well,
Because that's how I measure.
So I guess that
That's how well you can solve for y. Yeah, that one, it's way too tangled to be able to solve for y. All right, if you take the ln to get rid of the e, all of a sudden the other y is now inside of an ln. There's just no way to make it so you can get them together. So it's impossible to solve for y.
So let's just say that you could solve for y now.
If you could,
And my y prime has a y in it. If they don't say anything up there, if all they're asking for is y prime, do I still have to plug in?
no. It's okay. I wouldn't be that evil. Now, you always have to balance, right now, your learning procedures versus the real world. And of course, in the real world, you have software that probably does this for you, but we have to understand what the hell's supposed to happen. So in the real world, you just do whatever makes sense for whatever problem you got. So if you have an entire point, and I don't see why you wouldn't, it doesn't matter if you plug back in what y is. You just put the entire point's values in for both x and y. Who cares at that point?
Gotcha.
There's other situations where you want to compare derivatives and you want to be able to write them in the same form, and you might have to figure out what y is, but most of the time we just want to know what the slope is.
Okay.
Yeah.
I have a question on section 3.
Is that your question?
Yeah, but I have a different question. On section 3.9, 21. Now that triangle, would I have to figure out a squared plus b squared equals c squared, and then find the derivative of
You said 21, right?
Yeah, 21.
Okay.
The derivative of a, derivative of b, the derivative of c. Is that what I do?
Well, let's find out. Normally what you want to do is you want to figure out what function relates to everything that's involved. So what do I mean by that? In this case we have, this is number 21, page 249. At noon, ship A is 100 kilometers west of ship B. So here's ship B, ship A, and this is 100 kilometers. Ship A is sailing south, and ship B is sailing north, so this is going south at 35 kilometers an hour. Sailing north, 25 kilometers an hour. Is that mine? No, you're good. Okay. Let's see, where's this? How fast is the distance between the ships changing at 4 p.m.? So it's at noon. I was going to say, for a minute I thought they didn't give us any other time. That's kind of evil. But yeah, at noon they're this. This is at noon. And then at 4 p.m. they are something else. Here's B, here's A.
Can you just multiply the hours
Yes.
times the...
Good. I like it. So we can figure out exactly where they were. So this was A's position before. This was B's position before. Oh, good. Well, that's roughly right. Okay. Is everybody with me? So a little bit later. So 4 hours later, A would have gotten this far down. Exactly how far did A
B
get?
would have went up.
B would have went up. So there's two things you need here. You need a general relationship between the things you know and the things you don't know. And normally you want to find that first, because once you take the derivative, you start plugging in the actual values. You don't want to plug the actual values in too early, because then your derivatives become zero, where they really shouldn't be zero. You guys kind of with me? Yeah. If you plug values in too early, you get constants and they go to zero, and they really shouldn't yet. Hopefully you guys understand what I'm saying. Right. So here's the actual distance here that we're curious about. Let's use something other than D. We'll use... My brain had just said D for diagonal. That's still D, John. We'll use... What do we want to use? S. S is bad because it looks like 5. We'll use...
Q.
M. For slope.
That works.
Okay. So I need some kind of function that relates this distance M to things that I know, right? So when you said triangle, of course, what do you mean by that?
Two triangles.
Yeah, so you've got this distance here is 100 kilometers. You're going to know what this distance here is. You're going to know what this distance here is. But in general, let's see. I've got, if this is, I need more than this kind of colors. If this is x, then what's this going to be?
X minus X.
100 minus x is better. Right, because the whole thing's 100, so that must be the 100 minus that piece. This here we'll call, well, let's see.
You're going to know what that is.
Yeah, we're going to know what that is at that moment, but I need something in general, because I know how quickly that thing is changing. You guys with me? That's what I meant earlier about putting specific values in too early is bad, because then you're supposed to have a derivative there, but instead it's going to become 0.
I was going to say, when I worked it, that was dB of dt.
Good. All right. So we'll call this B, and we'll call this A, this distance here, right? Is that cool? I like it. So this M that I'm really interested in is made up of two hypotenuses, right? Hypotenuse.
You add the A to the B to make one triangle? Do it that way?
Yeah, you could, well, be careful.
Then you're using 100 for one leg, you're using A, B for the other leg, and you use A plus B for the other leg, and then you're using...
How do you mean exactly? It's hard to put those together and maintain that distance here that you want.
So you're gonna have to do two separate.
So it's okay.
triangles.
So what would this piece be here? What would this piece be here? This right here for that triangle.
H.
That would be b squared
So it'd be the square root of
first.
b squared plus 100 minus x squared. And this one here would be
A squared.
Square root of
squared
a squared plus
x squared.
x squared. So then my function, now there might be something better I could do with this, but let's see. The function I have so far looks like square root of x, a squared plus x squared plus square root of b squared plus 100 minus x squared. So let's do a specific example. Let's see if this looks right. Because at 4 p.m., so right now the only specific numbers I've used is the 100 kilometers, because that's a known fact. It doesn't change. Even as the ships move, that middle part is 100 kilometers. So its derivative is 0. It's not changing, right? That 100 right here in the middle. So I can use that to help me set these things up. But let's see, at 4 p.m., what are these values? At 4 p.m., what's A?
170.
Yeah, 4 times
140.
140 is better. I like that. So 140 kilometers. What's B?
100.
100 kilometers. So in that case, I've got this little triangle here that represents B is 100.
I have a question.
Yes.
So is that a constant then? Because that doesn't change. Is that going to be 0?
This middle piece would, but it doesn't show up in our... The only way it shows up is here. You with me? Yeah, so I don't have to really consider that. It's in there. But the point I'm trying to make is you can't use your values for a specific time too early, because then those parts that are supposed to be derivatives would become 0. That's what we were talking about earlier. I just want to say real quick why I was allowed to use the number 100. I have to use that value 100. That's really what links these two together, is the fact that this is 100 kilometers here. That's just always true. Okay, hold on. Sort of the same way we had a cone and the whole height was something and the radius was something. We use those numbers to set up what it was later. I mean, these are the same always for the whole thing. So that's sort of like a framework number. That won't change. Okay, let's see, where am I? And this, of course, is 100 minus x. And this is going to be square root of 100 plus 100 minus x squared. So I'm trying to figure out, is there a way?
Wait,
I don't like having so
how
many.
did you put that triangle together?
We have to have that many variables. But do we need the x variable? Is there a way to get rid of that thing?
You can make it one triangle.
That was-
A plus B is.
Because the length of A and the length of B are dependent on the time, and M is dependent on the length of A and B, but you don't want to know what M is until you know what time you're looking for.
Oh, I see. Okay, now visually I got what you're saying now. All right, so then we can look at this triangle.
Yeah.
Okay, so I was trying to figure out geometrically what does that mean? Because the first thing I thought of was this, and as I set it up, I didn't like how many variables I had. You with me? I don't want this x variable because I don't have information about. It's actually the derivative is 0 there, so that would kind of disappear. But it looked a little worse than it should have. So let's see. If I look at it here now, so now I have this thing. So this is 100, right? That used to be right here. Now just put it as the base of that triangle there. This piece is A and this piece is B. I like it. And this piece is the distance I'm curious about that I want to call M. Because D sucks, dt is always weird looking. I like that, that's better. And I personally don't mind when this happens to me. Now, as a student, it sucks when a teacher's work problem. They're like, oh, where the hell am I? But that's the first thing I thought of. But I stepped back and I said, I don't like how much crap there is here. There shouldn't be that much crap. Right? So you guys have worked this problem out. You figured out, yeah, there's one giant triangle. You got that makes sense. That I wouldn't need the x variable anymore. I just got one base to worry about. So now what's the relationship for what I really want here?
Square root of 100.
Yeah, m equals,
Square root
100 squared
100 squared.
plus B plus A squared.
cool, I like it. Now if you take that guy's derivative, you should have some dBdt's and dAdt's, and that's where the 35 and the 25 come in, right? Now am I catching up to the person who asked this question? Am I catching up to where you already were?
Yeah.
All right, good.
Like there's one similar like that, number 18, the base.
Well, wait. Let's see here. You should be able to take this guy's derivative now. That should not be a huge deal, even if it's a related rates problem. You rewrite this as
D of M over D of T.
in there. The 1/2, and when you take its derivative, 1/2 plot to negative 1/2, and then the inside derivative, that's nothing. That'll be twice B plus A times B prime plus A prime, or dB dt dA dt. You with me? That derivative should not be horrible. And then you know A, you know B, right, at 4 p.m., and you know dA, and you know dA dt, and you know dB dt. Is everybody cool with finishing that one out? You want to, it's okay to say right now, can you finish that one out? There you go. All right. So let me take away my first attempt here. So just to remind myself, dA dt was the 35, right? And dB dt was the 25. And at 4 p.m., A was 140, and B was 100 again. So if I look at this, what's this guy's derivative going to be? Let me be more specific. 1/2 this stuff.
Stuff inside. Negative 1/2.
I like it.
Times
0.
0.
0 plus.
Then I get twice A plus B. Is that cool? Twice A plus B. times, yeah, dA dt plus dB dt. And now it's just plug and chug, right? We know A, we know B, we know dA dt, we know dB dt. If you plug an A in, you get a number over there. Kick ass. Okay, cool. Because, I mean, in reality, I sort of hate having answers to everything already, because then that gives a wrong impression to a student that you're supposed to be able to set it up correctly in the first place. Which is not true. I mean, you set it up one way, you're like, I don't like that crap, and then you try to figure out, is there another way to set this up? And then you guys help me figure out, yeah, there is another way to set that up. But I mean, that's the kind of thing to expect with some of these problems. When you try to show it visually, your first attempt at drawing a vision might not be the best way to do it. Okay, so what was the other question?
The baseball problem.
Oh, yeah.
That 90 feet, is that just go away because it's a constant and it stays the same?
Yeah, that 90 feet stays the same, but he's running along that path, right? So, bless you.
And it said it was halfway to first base. So isn't that 45 feet?
Good. So somehow it's going to play
90
in.
minus X, right?
No, you know exactly what it is.
45.
Yeah, if they would have said at some point before he gets to first base, that would have been 90 minus X. You wouldn't know what it is.
Okay.
But here I know it's halfway, so you'll somewhere you'll need to put 45 feet. So this baseball problem, that's the world's most beautiful diamond there. All right. My diamonds have a few flaws. All right. So this is 90 feet,
And it's going, he's running 24.
and he's running in this direction at 24 feet per second. So this to me is sometimes the hardest part of these problems is you've got specific situation and you've got general variables that you need to take the derivative of. So I can't stress enough that you have to be careful about plugging values in too early. And really this question is about when he's halfway, the batter's the ball, blah, blah, blah. At what rate is his distance from second base decreasing when he's halfway to first base? So he's here. But that's actually too specific. I just want to know in general, what is an expression for this distance? And we'll call it M again. Why not? Now obviously, we have what shape here?
Triangle.
Triangle. Right. So in general, now here's where your question is really coming into play. In general, if he's anywhere along here, this is a constant. This, of course, is also 90. But this is changing.
As he's running.
And that actually has a lot to do with this. So as he's running, how far has he run in general? Not specifically, but in general. At some point, how far has he run?
12 feet.
In general. A t seconds later, how far has he run?
24 feet.
I love it. That's cool. But he's run
24 feet.
90 minus X?
X. Cool. He's run X feet. Right? So what's dx dt? 24 feet per second. So, of course, this piece is going to be, that's where your 90 minus X comes in. Yeah, okay. So you do have to have it come in somewhere. And the nice thing is here, I have a variable that I've had to introduce, but I have information about that variable. I know that dx dt is something. Right? Dx dt is given to me, 24 feet per second. So that's a clue to me that I need it. I didn't bring in a variable I don't really need. Okay, so what is this distance then in general for anything he's done from home to first? This distance would just be the square root of 8100 plus 90 minus x squared. Right, and then you take the derivative of both sides. You get your dx dt showing up somewhere. Throw in what you know. Then you can throw in the fact that you know that x is 45 when he's halfway. Good. Okay, maybe.
I guess I did this problem wrong, because I know that that's a 90-degree angle right there,
Yeah.
and then it's a 30-60, right?
Doesn't matter.
Uh,
Is it really?
Well,
Doesn't-
if that's twice the size of that, then it's a 30-60 knife.
But doesn't matter. Does it matter? If I had an expression about the angle, that might matter, possibly, right? But it doesn't matter in here. This problem doesn't care about the angle. They could have set this up as a problem about this angle here. At what rate is that angle increasing? But they did not.
Could you do it as base times height, and then do the product of that? Let's say that 90 minus x is b, and 90 is h, and then do the product of that.
If they were asking about the
Derivative
area,
of base in respect to t times the height.
now listen. If you do that, you have like a formula that represents
Yeah.
twice the area of the triangle. So they're not asking about some relationship about an area. That would be maybe Kepler's laws. If you ever heard of Kepler, how much area does something sweep out? I mean, there are things where we're concerned about areas, but here I'm only concerned about distances. So that's why we keep it with Pythagorean. That only concerns itself with first dimensional thing, lengths, right? I don't need to bring area into it.
Okay, I just have one more.
Is that cool with everybody? You guys able to finish that one out? It's basically a lot like the one we just did in form. Yeah. Okay.
How would you do 4 feet of the question?
So you do the same thing, except now you're related to third base. So part B would be looking at this. In which case, here's my right triangle. This is 90, right? Then you set it up according. Now you got x, not 90 minus x, right? Yeah. Okay, cool.
On number 4, would you use the product property or whatever it's called?
Number
4?
on the practice test?
No, on 3.9. Because it's length times.
So now they're talking about area. Yeah.
Yeah, it's length times width. So
Yeah.
you do d of L with respect to t times h. Times w plus d of w with respect to t.
Times L, and then you plug in the rates, you plug in the values at the time they're curious about.
What do you do to the d of a of d of t? Do you multiply that by a or
No.
No, you wouldn't do
That's
that.
what you want to know.
d of a of a d of a, and that'd just be.
It's asking you how fast is the area changing. So you're actually solving for dAdt.
Mm-hmm.
And that's what's nice about it, is you already have dAdt by itself, right?
Right.
So if you have area equals length times width, then dAdt, oh, that's a lot. dAdt, like you said, is L dw dt plus dl dt w. Yeah, right? And then you just plug in your values that you know. Cool. Yeah.
Can you do 1H off the practice test? I just have a simplification of issues.
Yeah, that one's gross. But it's nowhere near as gross as it first looks.
Okay.
Because the one thing, I actually did it both ways on the answer key, just in case somebody didn't notice. But anytime you have a derivative involving logs, especially, but in general this is true, but especially logs, you just take a second and say, can I simplify this first before I do derivatives? So what's the beautiful property of logarithms that really comes in handy?
Can you bring down that formula?
Yeah, so if I had like a natural log of x cubed, that's the same thing as 3 ln x. So I have natural log of 3 to the,
2 ln
yeah,
3 to the tangent of 5x minus 3.
so you could do it right the way it is. It'd be twice 1 over this mess times the derivative of this mess, and then you have to worry about 3 to the power's derivative is 3 to the power times natural log of 3. Are you guys semi with me? No? Do you remember 3 to the x? What's that guy's derivative?
3x ln 3.
Exactly, that's what I just said. Good. So that's part of what would happen to you if you did it this way. But what's one thing you can do at the beginning to make this a lot easier, based off of this? Bring that tangent stuff down front and with the 2. And then it becomes a nice product rule instead of an ugly... And what you're left with a natural log is a constant. That definitely kicks ass.
Okay, so since we weren't smart enough to do it that way, we did it the hard way. And I've got some really gross answer that I can't simplify down.
Well, here, let me go ahead and give you guys the answer key. Because I'm thinking to myself, I already did that problem. Let me give it to you. I don't want to duplicate my answers here. Let's see. Right.
Mr. Waller, your handwriting is pretty.
Yeah. All right, so you're talking about age. So it's right at the bottom of the first page. Can you follow along that trail?
Okay, so I have the same trail.
Okay.
The answer that I come out with when I compound that trail is 10 secant squared to the 5x minus 3 times 3 to the exponent of the tangent 5x negative 3 ln 3 all over 3 to the tangent 5x to the third. I don't know how to get to...
Well, you see how you have 3 to the tangent blah on top and 3 to the tangent blah on bottom? Cancel this, right? You see that's all multiplication on the top, right? So, and you have it on the bottom, so just cancel.
I hate it when it's that.
Yeah. But the test, you didn't cancel it. I would just point it out. I wouldn't take points off because it's important to see that when it happens. But you get to the point where you're so afraid because normally it's not allowed because it's got like plus some other crap, and so you've gotten to the point where you're like, I never do that now. But I mean, that's a place you can totally do it. Yeah. And then the other way is like a one-liner, right? So the big clue there is if I give you a log derivative, more than likely, if you simplify it, it'll make it a lot easier to do. I won't make it, it's not impossible to do it the way I give it to you, but it's a lot easier if you simplify first. Right? Unless you forgot how to simplify logs. Then that's bad. Yeah.
Can you do number 40 on section 3.9?
Oh, and by the way, before I forget, we're going to do number 5 on the practice test, 101 and 102. I got to the end of my third page for the answer key, and I didn't want to start a new, so we'll just do that together on the board. You with me? It's not on the answer key.
Right.
Number 5, number 101 and 102. We'll do that on the board. But what are we talking about now? 39, 40? Oh yeah, these lighthouse problems. Lighthouse on a small island 3 kilometers away from the nearest point P on a straight shoreline. Okay, so we got a little lighthouse. And then that looks really bad. Let me try it again. It looks like something entirely different. So I just have a lighthouse. And 3 kilometers away Here's point P. Its light makes 4 revolutions per minute. So it sweeps up 4 revolutions every minute. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? So it doesn't matter if you're 1 kilometer up or down. That's why it doesn't specify. So I'm just going to put a 1 kilometer down. So does this make sense? So if you sweep your flashlight along, it's going to be moving along the wall at a different velocity. Your velocity is the same, but of course it's going to move at a different velocity along the wall the further away it gets. Does that make any sense at all? Okay, good. Hopeful. So I've got, this thing is turning around 4 revolutions every minute. So after a minute, it's hit point P 4 times, right? So at this point, its angle is changing by some d theta dt. So it's got some rate of change of the angle at that point. Okay, so again, I want to set up a general formula that relates the variables I know and that I know values for and that I don't know values for, and then I take its derivative. It's really sort of the same idea every time. So what relates, now this doesn't change. That's solid. I want to know at a time when it is 1 kilometer away, so in general, how far away is this? X, I like it. Cool. You guys with me? So that is actually really important to be able to identify what's my set things and what actually is changing. And the value of 1 kilometer is way too specific to use too early. It's at a time when it's 1 kilometer away, so in general, it isn't. So I need to know that's X, and then later I'm going to plug a 1 in for that. Do you guys see that difference? You say that's key for this kind of problem, and it's really easy for me as a teacher to forget to say that because it's almost second nature to me now. But that's what you got to be careful about when you're setting this up. Now, what relationship can I use between the angle, the 3 kilometers, and the X?
Tangent.
I love it, right? Tangent. So tangent theta is what?
X over 3.
I like it. In general, it's X over 3. Cool.
Where'd you get that 3 from? Oh, I thought that said 36. It looks like 36 for some reason.
I got you.
You did get me.
All right. Everybody with me so far? And I don't see how you could do some of these problems without drawing a picture of some kind, right? And obviously, it doesn't have to be pretty, right? Your little lighthouse, mine at first was offensive. I don't know if any of you guys saw it. So I had to draw a little box. That's my lighthouse. Didn't, you know, I don't know if you ever saw the lady talking about the traffic and she draws something, but look it up. It's on YouTube. So now I've got my relationship. Now I can just go ahead and take derivatives. So the whole purpose of this problem, I think, is just to, do you know how to take the derivative of tangent? What is the derivative of tangent? Now what do you have to be careful on when you do that? What do you think the derivative is respect to? T, not theta. So what has to happen here? D theta dt equals, and it's sometimes easier to write, instead of writing it as 1/3 x, because for some reason it confuses people when it's x over 3 looks like a quotient or something. 1/3 is just a constant coefficient. So what's the derivative of 1/3 x? 1/3 dx dt.
Your dx dt is 1. Right? So,
No, you gotta be careful. Which thing do I not have? What am I trying to solve for?
The speed of the change of light.
Oh, that's actually decreasing.
Yeah, so here's a good thing. So, what is this? I forgot, but in the very beginning, when you write down what it tells you, you should put symbols on it right away. So what is that? What Leibniz notation represents that? It's not a length. It's a sweeping out. It's an angle change, right? So in a way, it's d theta dt. Right, you can turn it in terms, if you want it in terms of radians, one revolution would be 2 pi radians. Right? So if it's 4 revolutions per minute, it's 8 pi radians per minute. It's still a d theta dt. Are you guys with me? It's definitely not a straight length change. I wouldn't say, how fast you run? I ran 18 revolutions of an hour. What? You did what? Sorry. History people are like, it normally takes years for just one revolution. To me, the hardest part of this problem is something I said earlier, because I really didn't think ahead to what was going to happen with the derivative. But now I look at this and I know they're asking me about how fast is this distance changing, right? They're asking me about this. Okay, there's that. They gave me this. Okay, there's that. What do I not know to solve? This should be the only thing I don't know. What else is in there that needs a value?
Theta.
Theta. So at the time when this is 1, can we figure out a value for theta?
Yes.
Hell yeah, we just use the equation actually that we already have. So tangent theta, at the time when this is 1, tangent theta would be 1/3, right? And you could actually tell you honestly, you could just do this. Let me see if you guys are with me. What would secant theta be for this triangle? The way it is, with the 1, the 3, what would secant theta involve? Secant theta is 1 over cosine, there we go, right? And cosine needs this side and this side, right? So secant would be hypotenuse over x. What's the hypotenuse when this side is 1?
3.
No. Square root of 10. 3 squared plus 1 squared equals that. Square root. So you get root 10. So what is secant theta then? At that time. Secant theta is... Try it again. That's cosine. Root 10 over 3. Now let me just stop right there. Let me stop there for a second. So again, is everybody cool with... setting this up wasn't that difficult, right? Taking this derivative was not difficult, because we all know the derivatives involved there, right? Stepping back and figuring out what it is I don't have a value for yet. That sometimes is freaky. But then you just say, at a time when this is 1, can I figure out what secant theta is? Well, I know tangent theta is 1/3, but even better, just finish out the triangle at that time. This will be root 10. So secant theta would be root 10 over 3 squared. What's d theta dt? 4. Good. Revolutions per minute equals, and then multiply by 3, and that'll be dx. Right? Multiply by 3, that'll be dx dt. Okay, maybe. I like this kind of problem, just to let you know. Which would translate into this kind of problem will be in the test. Not exactly this. What do I mean by this kind of problem? A problem where you have to figure out when they tell me at a time when this is blah, can I look at my function that I got the derivative for and see what is it I don't know and how is it related to that? Right? It's not always going to be just a straight up plug this thing in. Very often it is, but not always. So I foresee at least 2 related rates problems for you guys. One that's a little bit more straightforward, and one that involves something like, how do I use the value he gave me to give me what I actually need for this function, or for this relation? Yeah. Okay, cool.
So, what the answer is in revolutions? That's revolutions per
Exactly.
minute.
And they don't ask for a velocity units, so that's exactly the units I'm going to use. Well, what suck here is if they put on top of it like it wouldn't suck really, but if they put what's the word, conversion problem on top. Is it, what's the velocity of the, in degrees per second? That would be kind of evil. Yeah. But they did.
It's not kilometers per minute? Since X is kilometers.
Oh, X is, yeah, we're solving for dx dt. This will be in revolutions per minute. So let's see, let's be careful about this then. Revolutions per minute. This is in,
Since X is kilometers.
So what is
so, let's see. I gotta think about it.
Well, if the rad 10 is
that a portion of
kilometers, or, I'm sorry, no, rad 10 is gonna be, the rad's gotta cancel out somewhere.
Now be careful. This is always going to be unitless. It has to be. Your trig functions are always going to come out unitless. So it's always things that they're multiplying by that give us the units that we need. I just got to think about.
What was the 1/3 then? Why?
That was just.
That's
Yeah,
ratio.
Yeah. That's.
That's 1 kilometer over 3 kilometers. The kilometers would cancel out.
Oh, of course.
That's what I'm trying to find out.
Gotcha. This is 1/3, but this is 1 kilometer, 3 kilometers. Yeah.
Something's either gotta wipe out the rev or it's gotta wipe out the minute.
Correct.
So maybe it is a. I got to think about it. Is it also a conversion problem on top?
If it's 4 revolutions a minute, then it's 8 pi.
Yeah, it's just 8 pi, that's a number, isn't it?
No, it's 8 pi radians,
But they're asking.
but they still need kilometers. So I mean, if we had a circumference kind of thing, we could figure out the circumference thing. But that doesn't make sense here because it's constantly changing whatever circle we want to consider. So it has a radius of 3 here, but then it has a radius of root 10 there. So it doesn't really help us to think of it that way. So let me think about that one. That definitely was a little more involved than I at first realized. Because it doesn't make any sense, like you said, it doesn't make any sense for our units to be revolutions per minute when we're talking about just a straight change. But we'll come back to that one. Let me let my subconscious work on that, hopefully. Yeah.
Isn't there something where you could take like the arc of it?
Well, again, it's got to be like a set circle, and my circle is constantly changing. Does that make sense? I mean, it's depending on where I am on the shoreline. In fact, it becomes infinitely large. If the shoreline was infinite. Something stupid, easy. Which number is this?
40.
Yeah.
All right, I got to think about it. Let's move on for right now. But there's one little thing, I'm sure some stupid little thing to make it to the right units. I just can't think of it right now.
Or is that something that has to do with making it a related rate problem? That makes sense.
The unit is still across. So like right now, if you wrote
Well, related rates just refers to the fact when you take a derivative of both sides, you end up with a relationship between rates. So that's all that refers to.
That's just ask another question about another delivery problem. But
All
it's
right,
like,
good.
It's like much simpler. Like it's just I just need help setting this up. I guess. I mean, it's number 15 with the cars going in opposite directions. I just kind of need help with setting it up. I still don't really get
is
it.
that the one where they start
Is that A squared
plus
plus B squared plus C squared?
Yeah, so two cars start moving from the same point.
Oh
Oh, yeah.
South.
So one's going south and one's going east or something, right?
How's the hypotenuse? But I don't
West at 25. So this one's moving south at 60 mile an hour,
Yeah.
and this is moving west at 25. I can't let that one out of my brain. So in general, the relationship here, this one we can call X, we can call this one Y. So this distance between them, which can use M as one. Yeah. 2 hours later, we'll eventually have to worry about that. So right now, so I know that 25 is what in symbols? dx t 60 dy dt the same way. They're asking me for dm dt. This kind of thing is stupid useful, by the way. Right? Just writing what you know, what you don't know. So when you set up your equation, you know exactly what it is you have to figure out, and what it is you can just calculate. So of course the relationship here is
A squared plus B squared plus C squared.
And by the way, with any of these that we did with triangles, you could do implicit differentiation. You can leave this side squared, but why do that? You just do this. Yeah, exactly. So I can have this as 1/2 power. So I mean, this isn't too bad, right? This is almost like the ones we did earlier. Is this okay, guys? Could you finish this out? I mean, now we can do what? Take derivatives.
Because it becomes 2x. Well, I mean, after you do the initial derivative, the second one, the chain rule, it's just like 2x times dx over dt, right?
I like it.
And that becomes 25 later on.
Doesn't become 25. It is set to be 25.
Oh, yeah.
Yeah.
So yeah, you just plug them in.
So plug the 25 and plug the 60 in. X, of course, since it's 2 hours later.
Okay.
At 2 hours, X will be 50 and Y will be 120, right? 2 hours later? Yeah. So you plug all the stuff you know in there. So you know X, you know Y, you know X, you know Y, you know the rates. So you got everything you need to figure out the MDT, and thankfully here, all the units are the way they're supposed to be. That's really bugging me. Yeah.
I just have after you find the answer for number 2 on the practice test, you'll end up with function, and the function that you begin with, and the tangent line. If you plug x into both of those, in this case 2, and they both give you the same answer, that means you have the correct line. Correct?
You could always have two mistakes that cancel each other out. I mean, so I would never say yes to that question because, there's always, somebody always says, but it comes out right when I do this, but say everything in the middle is wrong. So I don't care what it does at the end. But I mean, on that kind of problem, if you did everything right, it has to. So if it's right, then it must do that. But if it does that, is it right? No.
Okay.
Logic would not say
no,
that.
That is exactly why I asked that question.
Good. I like it.
Are we going to expect to find the derivative of a log with a base of like 5 or something?
There is. I don't think we went over it, but the rule for that. In fact, if we try to derive it, let's do that right now. So if I had a function, let's use y. Y equals log base b of x. Let's try to figure out its derivative. Because I think when I did this, I just did natural log right off the bat. I didn't even talk about this, but it's in this section. So I don't know log base b's derivatives, what I'm trying to figure out. So what could I do to this? Turn it into a problem whose derivative I know, right? Sort of like when you have an area you don't know, you try to cut it up into areas you do know. So here, how can I rewrite this in terms of a function I do know its derivative? Yeah, b to the y equals x. Now taking both sides derivatives, what's the derivative of some b to the y power? Itself, ln b, y prime. Sweet, I like it. All right? This was the rule for this type of thing, and this is chain rule. Right, the inside gets a turn. Equals 1. Because y is a function of x. Cool. Now if I solve for y prime, I get 1 over b to the y ln b. But what was b to the y? X. So I get y prime equals 1 over x ln b, which might make sense if it's ln. If the base is e, this piece would go to 1. So the derivative of ln would be 1 over x, which we know is true, right? So I want you to really see this. If I have 2 to the x, its derivative is what?
2x ln x.
ln of 2, yeah. ln 2. If I have, where are you going with this, Jeff? Log base 2 of x, its derivative will be 1 over x, that's the derivative of any log. But just like here, you have to do natural log of the base, if the base, even if the base is e, just as 1 if it's e. Same thing here, you have to do natural log of the base. It's a really nice analogy between them. Usually you would expect it to be somehow related, because those functions are inverses of each other. They should be somehow related. Does that make sense? Okay. Yeah.
I just have a format question on that. So, because we began with y equals, and then the variable x is within that problem, and they say find the derivative, it's implied that it's derivative.
Yeah, they don't have to
x.
say. They don't have to say here what's a function of what. But even if you give you one with y and x tangled and they don't say, we have to assume y is a function of x.
Okay, so that's the...
It's on them. It's on the book. It's on me to make sure it's understood if it's not that way. Does that make sense? So like WebAssign made it very clear. I want you to find dx, dy instead of dy, dy. They had to, because otherwise you just assume it's y prime is dy dt, or dy dx, and x prime is 1. Okay.
Hey, this one?
Yeah, God, I gotta leave that there for. I'm not gonna erase that. I gotta figure that out. Okay, so let's do this. Before I forget, let's do the last 2 on that practice test. That's not on the answer key. So on page 262, it's number 101 and 102. Or 265. So this is actually page 267. Of course. Angle of elevation, you have angle of elevation and angle of depression. So if I'm standing over the Grand Canyon, my angle of depression down to something stuck in the side is always based on straight off, horizontal. So angle of elevation is defined to be between horizontal and the thing I'm looking at. So that is decreasing at a rate of 0.25 radians per hour. Sounds a lot like that problem. So let's see what happens here. So what would that be in symbols? Good. D theta dt. How fast is the shadow cast by a 400-foot tall building increasing? So let's put that 400 foot. Here's a 400-foot tall building. And its shadow would be here. So how fast is the shadow cast by a 400-foot tall building increasing when the at a time when, where'd it go? The angle is pi over 6. Alright, so this seems a lot like that one. So, in fact, what's the relationship I can set up here?
From the height of the sun to the height of the tangent building.
Well, I don't need the height of the sun, thank God. Right?
Okay.
You mean like the angle?
Well, I
Well,
was trying to make 2 triangles, but...
oh, this is not a
related
situation like a tree and a person or something. the sun is providing just this. As the sun moves, this changes. So that's all I need to know about the sun, is it's providing me the angle. As I look at the sun, and my angle is decreasing. But what's the relationship within this triangle? Okay, tangent theta.
400 over x.
400 over x, cool. Right, so x equals, I like it. So instead of dividing by tangent, I can just multiply by cotangent, or, just reciprocate tangent. Because we know cotangent's derivative, right? Tangent's derivative is secant squared, so cotangent's derivative is negative cosecant, because it's always negative for the cotangens, right? Is everybody with me so far? So when you take this guy's derivative, implicitly, dx dt.
Minus 400.
Yeah, so negative 400. Just like we said, cosecant squared theta.
D theta.
Yeah, good. The inside's got to get a turn. D theta dt. So every variable that is changing over time has to have its turn, has to have a chain rule piece come out. Okay. Thankfully, our building's height is not changing over time. That would be bad. Sinkhole or something. So,
How did you do the cotangent step? I didn't understand.
well, tangent theta is that, so cotangent theta is that. Is that cool?
Oh, yeah.
Yeah, and then just multiply 400 up.
Okay.
Really doesn't matter which way you do it. It should come out to the end, same thing at the end. But it's a little better to have something not on the bottom, right? And now, what do I know? I know this. Anything else I know? I'm trying to figure out this here, right? How quickly is my shadow's length?
Theta.
I know theta, which kicks ass. I know what I need to know, yeah. What's the 400 in terms of? Feet, right? And this is, I'm trying to figure out, is that what saves our ass over there? But I'm trying to figure out. This is unitless. So this is feet times radians per hour. And do you guys remember radians? Just kind of get out of the way. Arc length is S equals R theta. You guys, so if I, all right. So if I had a radius of 10 meters, and I want to know the arc length if the angle was pi over 2, let's say pi over 4 radians. The arc length is r theta, right? Stay with me now. So it's 10 meters times pi over 4 radians, right? So it's not meter radians at the end. You wouldn't say you have a meter radian length. The radians disappear. So radians are placeholders, really. They're not true units. They're because this is it's kind of like a how could I say this? It's like a based on the unit circle. So when I multiply by something, I'm scaling it up to that. So that just gets out of the way. That's not there anymore. It's not 1. It's 10 meters worth. So does that make any sense at all? You should have addressed this at some point in your history of math. Okay, so that's just to illustrate what happens here. So this looks good. We don't have the same problem we did over there. Maybe we don't have a problem over there. Maybe I'm making too much out of it. But here I got feet times radians per hour, so it's going to end up in feet per hour. With me? I like that. She's
No, I mean, it's just the question is, how fast is the shadow cast?
yeah, exactly. So I've got the dx dt, but I'm just over there. We seem to have some trouble, and maybe we really don't. That's what I'm trying to say. So we'll have to look at that again. So here you just plug in what you know. Negative 400 feet times cosecant squared pi over 6 times 0.25 radians per hour, right? What's cosecant of pi over 6? Cool. 2. Because cosecant is 1 over sine. Sine, when it's close to the x-axis, is small, so it's 1/2. 1 over 1/2 is 2. And be real careful. I just made a mistake up here, of course. I love doing that. What did they say specifically about the angle? How is it changing? Decreasing. So what should be here that's not there? Negative. So now you get 1/4 of 400 is 100. The negatives cancel. This was 2, so you get 200. Well, this is 2 squared though, right? So we get 1/4 of 400, you get 100 times 4, so you get 400 feet per hour. So over here, I think I've figured this stupid thing out. The equation really is x equals 3 tangent theta. This, is, of course, is in kilometers. Problem solved. So, you guys with me? I mean, no, you guys are not with me. So all I did was pick this thing over there. So now when I do this, I'll get dx. It's the same thing we did there. It's the exact same math. It's just I put the 3 over on the other side. But it's got kilometers. So when I do dx dt, I'll get 3 secant squared theta d theta dt. So this will be kilometers per minute in this case. It was because I left this 1/3 here, we thought that, that they do go away, but actually if you bring the 3 over, it's got its own kilometers. It's fine. Maybe not.
So, say that again.
So there was no problem here. You with me?
Right.
There was no problem here because we have an equation solved for x. When I solve for a trig function must be unitless. Must be. In fact, its input must be essentially unitless. And I just basically made a case for the fact that radians are actually non-units. They're sort of placeholders. So this is unitless, so this side must be unitless. So if I leave it like that, I have trouble at the end figuring out what happened to my units. Whereas, what do we do in the next step? We solve for x. And this carried the feet. So then I get feet per, what was it here? Hour. So I have the same thing happen over there if I would have just put the 3 on the other side. So it was a non-issue, actually. It's just the weirdness of trig functions that they're unitless.
So the revs per minute or
What
the
did the
that was
Yeah, revolutions are a non-unit. Yeah. And actually, we might have to put in here, now that I think about it, we might need to put in there, what did we say earlier? That would be 8 pi. Yeah. Radians. And you just multiply all that together.
What happened to the pi over 6 again?
We had cosecant of pi. Yeah, just plug it in for cosecant. And cosecant of pi over 6 is 2.
Okay.
Yeah, 2 squared gave me the 4.
1 over 1/2. Right.
Yeah, 1 over 1/2, exactly. And then square it. So that's where the 4 came from.
Ah.
Cool. Okay. Good. It always sucks when I explain something and that actually made it more confusing. But that was the problem over here was when we have it solved for the trig function, it's unitless. So later it's a little weird to try to collect the units back up. Whereas if you solve it for the variable, it's not unitless. It's actually carrying the units here. X is in kilometers. This side is in kilometers. Okay, that's not a point that's ever made anywhere, but there it is. So the other one, that was number 101. Let's look at number 102. Oh, and this is a linear approximation problem. And I don't know if I managed to get any people as excited about some of the stuff I was excited about last time, but the basic idea of linear approximation is I can take a function and say it's approximately equal to, and who remembers, this is really just the mx plus b formula, well, the y minus y1, that one, but how does this thing work? So it'll be at a point A, or near, let me say near, of point A. A function is approximately equal to what? Good. F of A, that would be like y1.
F prime of A.
That's your m. X minus x1, so x minus a. So there's my y minus y1. We just moved the y1 over. Equals m times x minus x1. That's all that is. So on one level, it's almost too easy. We've already been doing this. It's just the equation of the tangent line, really. So in this problem, it says, find the linear approximation of f of x near 3. So they give me a function. So I need f of a, which is f of 3. So I just start looking to see what do I need to fill this out. What's f of 3? 4. I like it. 25 minus 16. What's f prime of x? Let's write this like this.
1/2.
Good. 1/2 of this mess to the negative 1/2. Cool. You guys with me? And again, this whole problem requires you to remember this form. And if you forget this form, just write y minus y1 equals mx minus x. Well, I spur you into how it works. And then you just collect. You just start calculating all the things you need to put that together. So just cleaning this up a little bit. I've got, those go away. So I got negative x over the square root of 25 minus x squared. So what's f prime at a, which is f prime of 3? Well, the bottom we know. We already did that. It's 4, right? And the top will be just negative 3. So I get negative 3/4.
Can we do one more of those?
We're not done with this one. Well, we will. Yeah, we'll do another one. So now I've got everything I need to put that together. So near 3, the square root of 25 minus x squared is approximately equal to f of a 4 plus f prime of a, so it's actually minus 3/4 x minus, and what's a again?
4.
No, 3.
3. Stay with your first instinct. 4 was just an outcome of it. A is near point A, near 3. This is all about being near 3. So take a second. If I plug a 3 in, now watch how this is kind of nice. If I plug a 3 in, what happens on this side?
0.
That correction piece becomes 0, and of course that becomes f of 3. It's exactly the right value at 3. If it's supposed to be close to right near 3, at 3 it better be freaking right. So I like to look at this piece as a correction piece. And actually that's exactly how to look at it. You guys, let me this is almost too cool to not talk about. But you can get a better approximation. Let me just, real quick, see if you guys can stomach this. If you go to the next derivative up, and you might be able to imagine why there has to be an over 2 there. It kind of goes along with that. This might be a little too far ahead, but this is actually the next correction piece. So if you go into physics at all, this would be called permutations. It would be you start with your base idea, and then you start messing, you start throwing in more conditions, and it just goes further and further. So you could actually get a slightly better approximation if you go out here. And this is sort of almost related to doing like a linear fit. Have you guys ever, any statistics people? No, shit, all right. That entire line of discussion, I'm not going to go down. Nobody would know what the hell I'm talking about. But this would be related to fitting it with a, this would be a linear fit. Well, this would be a linear fit, so this would be a quadratic fit, like a parabola. All right, so all that you have to know. Okay. Let me take that away. And if you get into Calc 2, you'll talk about that actually with infinite derivatives. Yeah. Well, right now we'll just stick with the first. So that's part A, is just find the approximation. I love the way that you guys just silently like, he'll be done with this in a minute. All right, getting back to the problem. Illustrate part A by graphing f and the linear approximation. So if you just put that in your calculator, you'll see the square root of 25 minus x squared would be like the top half of a circle of radius 5. So if you graph that, it should look like this. And then at 3, so it should have a, if you did 4 minus 3/4 x, so let me see, what does this come out to be if you do this? 4 plus 9/4, 25/4 minus 3/4 x, and that's just a little over 6. So see how that kind of makes sense? Here it is like this. Giving me board license on that actually kind of makes sense. That's the y-intercept. Is that cool? The square root of 25 minus x squared, you should be able to think that's the top part of a circle of radius 5. Is that cool? So my ugly ass sketch, it actually kind of makes sense. What I end up with, that line would have a negative slope starting at a little above 6. It would hit that once there. That's 3. Okay. So that's what you should see in your calculator when you graph this. Okay. How are you feeling right now? This is review night, so you have total rights to say what the hell just happened or anything, because you guys are looking like, yeah.
Yeah, everything pretty good except for 3.10. I don't really get this stuff.
The linear approximation stuff.
Yeah.
Wait,
Yeah, this is section 310.
which one did we?
We haven't done 311 yet. That's the hyperbolic trigonometric functions. Yeah. 3.9's related rates. Yeah. Yeah.
Wait, why isn't f prime a 0?
Because I have to know what f prime of x is first. See, this is the whole thing about plugging a value in too early. If I plug 3 into my function, I get a number whose derivative is 0. But what does f prime of 3 really mean? Find f prime of x, and then plug 3 into it. Does that make sense?
Yeah.
So in general, if I see f triple prime of 7, I have to work with f of x, f prime of x, and then get to f triple prime. I cannot evaluate that function until that function exists. So I have to first create it, find out what it is, and then plug a 7 in. Because if I plug a 7 in too early, all my derivatives are 0. Every problem is easy in that section. Because that section's coming up. So you gotta be careful. The problem's easy, but it's also wrong. That's not good. So that's part A for that problem. What about part B? Oh yeah, part B was the graphing. We looked at that. And in part C, you have to do that in the calculator also. Do you guys want to look at that? We might as well pull that up. My worst fear on review night is to waste your time. I want you to get something out of it. We can do this semi-quickly here.
Yeah.
Oh, okay, well, we can only move so fast. Because you know I'm going to ask you a question on the test that has you do exactly what part C of this wants you to do. We did this once last time. Remember, it's finding the values between which the approximation is good within something. So part C says, let's just write it out up here real quick. Part C says, For what values of x, and I don't know why they always pick 0.1. Seems to be a normal standard thing, but for what values of x is this good to within 0.1? So remember, this whole thing was about, I want to know where's it there?
Deltas.
I want that distance, oops, sorry. The distance between the approximation and my actual function, I want it to be less than 0.1. So I want my function to be within root 25 minus x squared minus 0.1, root 25 minus x squared plus 0.1. Let me just stop right there. You guys cool with what I just did? Because you can rewrite this as negative 0.1, less you go this, less you go that, and then you add this to both sides, and there you go. You can pretty much jump straight to here if you remember that, right? I want my approximation to be no more than 0.1 away from what it's supposed to be, and no less than 0.1 away from what it's supposed to be. Right? So it actually makes sense just to go right here, because that's exactly what the hell it's saying to do. Okay, maybe. I love it. I can never tell if some of you guys are humoring me. Sure, you make sense. Or if I actually make sense. Pretty much sums up teaching right there. The coach was challenging.
Did you not do this part with that calculator? You have to have a calculator first.
Yeah. I mean, solving inequalities by hand that has different expressions for x on all sides. Almost impossible. You need a numerical method to solve it. Okay. So here's how you do this. You can put in the floor, which will be the root 25. Where am I at? Minus 0.1. Then we have our approximation in the middle. 25 fourths minus 3/4 x. Then I have root 25 minus x squared plus 20. That's my ceiling. Alright, you guys with me? Okay. Of course, it all depends on what window I've got here. Let me see. Turn this thing. Stop it. Stop. Okay. Let's come to the standard window. So there's my top part of my circle. There's my approximation. And now you see that I can see where I need to zoom in now, right? Are you guys with me at all? I mean, if that's a circle, that's a little bit larger radius circle. That's a little bit smaller radius circle, right? Or it's actually lifted up and down, but it's not really radius change. They're so close together, of course, that I need to really zoom in on the important piece, which is where does my approximation intersect one of those two? So this is where I use my favorite thing on here, which is zoom box. Or can you zoom in, whatever works best for you. Okay, so now I should be able to. So there's the floor. There's my approximation. And there's the ceiling. So it looks like it hits the ceiling. I might even want to zoom in one more time. But what's important here is the process. This is what you have to do. So I'm going to zoom in one more time. And it looks like the important one is the ceiling. Nothing more exciting than this. Alright, maybe that's going to be good. Let's see. Alright, there's the floor. My approximation.
Once you realize you just need the ceiling and tangent.
Yeah, you're right. I could have taken that out of there. I should have. But now I can see my two intersections, right? There's one intersection, there's the other intersection. Do I need to do that right now? Can you guys find intersections between things? And like you're saying, like Dan's saying, once you figure out it's just the ceiling that matters, then go ahead and go back and delete the floor. So you don't have all this crap to look at on the screen. It's not a bad idea. So now you would just find, it looks like a few of you guys are looking at like, please keep going. So to find this intersection over here, you got to make sure, since I did not delete my floor, because I am not the brightest person, I want to find the intersection between my approximation. So I'm making sure that there's my approximation and the ceiling. Good. So just make sure before I hit enter that I got the right functions I want. And then my guess, I already put it on my guess. And there's the lower value. So it looks like I did it around 3, so I should expect it to be, from, in this case, it's 2.2 up to who knows. It doesn't have to be symmetric, obviously, because my functions are not going to be linear. You guys, it sort of reminds us a little bit of the delta stuff, but not really. It's nowhere near as hard. We're just getting everything from the computer. Okay. So you do the same thing for the other side. You get that, and then you say it's within 1.1 of the right answer from 2.23 to blah. That's how you would answer that kind of question. Okay, good. All right.
There's always only going to be 2 intersections, right? Because
it's linear.
Trying to do this, even if it does this, we're only trying to find.
We will always have a straight line approximation.
Yeah.
So, and we're only talking about. I see what you mean. I mean, if we have a function that's going insane.
Yeah.
And I already told you I wouldn't do that too. But in general, if I did, how can I say this?
You just got to shrink your.
You have to get, because you'll see if you go in close enough, you'll see where it gets really far away and then it comes back again. So you always want to do something around the point that you expanded it around.